All right, so in this video, we're going to talk about the derivative as a rate of change, which it is. I've said it all along. Derivative is a rate of change. Primarily, we study it as an instantaneous rate of change. That's always what it's been and always what it will be moving forward. But there are some interesting context that we can view the derivative. So I'm going to go ahead and start off by saying let s equal f of t be a position function. So it's going to be the position of an object at time t. So s equals f of t is a position function at time t. Now, if we go ahead and move forward by taking the derivative of s with respect to t, right, that's going to be the derivative of s with respect to t, which is ds dt, which is also in different notation, the s prime of t. The change of position with respect to time. Think about that in the most intuitive way possible. If you're changing your position with respect to time, what are you studying? Well, at that point now you're studying a velocity function, v of t. So the f of t is the position, the v of t is the velocity. So let's go a little bit further. If we take now the derivative with respect to t of that velocity function, which is your dv dt, which is your v prime of t, what do you suppose that is? Well, that's going to be your change of velocity with respect to time. So again, break it down fundamentally. If your velocity is changing with respect to time, what are you now going to be studying? Well, now you're going to be looking into the acceleration at time t. So if we've got a position function and we take its derivative, we get a velocity function. If we take its position or its derivative, we get an acceleration function. Now there are a few more things worth mentioning in here. Velocity and speed are different, and a lot of times they get kind of used interchangeably, but they're not. When we talk about speed, for example, speed does not have direction with it. Velocity does. You can get a positive or negative velocity, but you can only get a positive speed. So in that sense, the speed is going to be the absolute value of the velocity function. So make sure you're okay with that. The velocity can have direction, but the speed cannot. It's always going to be positive. A few other things that I'm just going to mention briefly on the screen. The book talks about displacement. Also talks about average velocity in more detail here. Both of these things were studied earlier in the course. We didn't necessarily use the name displacement or average velocity, but if you go to page, what page is that? 124, you can see that broken down for you now in a more traditional way that we would have been using the notation. The other thing that the book talks about is jerk. Jerk is actually going to be the change of acceleration with respect to time. So the change of acceleration with respect to time, which would be your a prime of t, which would equal the jerk. So we could continue that further as well if we needed to. That's discussed a little bit on page 126. But my primary focus is generally going to be on position, velocity, and acceleration. And we'll see this stuff again later in the course when we transition into integral calculus as well. But review those pages, review those concepts. I'll go ahead and clear the screen and we'll take a look at an example. Okay, so in this example, I guess this is out of your text. It's a word problem. I'm definitely not going to put all this on the screen. We don't have any place to write. And so it's on page 130 of your text. It's number 10, lunar projectile motion, and states a rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second reaches a height of s equals 24t minus 0.8 t squared meters per second, or no meters, sorry, it's a position. So s is the position function, and so that's really about all we need to get started with a problem like this. In part A, it wants us to find the rock's velocity and acceleration at time t. Okay, so find the velocity and acceleration. Well, we know that if we take the derivative, s prime, that's going to give us our velocity at time t. So all we need to do is multiply down and subtract 1 all the way through. We'll get a 24 minus a 1.6 t. Units on this guy would be meters per second. For not part B, that's actually the same part. They want the acceleration. So if we take the derivative of v, we're going to get the acceleration at time t, which in this case is just going to be negative 1.6 with units meters per second squared. Okay, so really nothing there other than taking a couple derivatives. So part B then follows it up and says, how long does it take the rock to reach the highest point? How long does it take the rock to reach the highest point? Well, if you throw a rock vertically upward from the surface of the moon, it's still going to come down eventually. And so as you throw this thing up, it's eventually going to come down. Where is it going to reach its highest point? It's going to be right here. And where is that? Well, what is the velocity when you reach that highest point? It's 0, right? It doesn't happen long, but for an instant, our velocity is 0. So the instantaneous rate of change would be 0 at that particular point. So I'm going to take v of t, and I'm going to set it equal to 0. That would give me a 24 minus 1.6 t equals 0. In other words, t equals 15 seconds. Okay? Letter C. How high does the rock go? Well, how high is a question of position at this point. And so what we're looking for now would be the position of the rock at 15 seconds. We're here, we're in this position at 15 seconds. We know the velocity is 0, that's where it would change from going up to coming down. So that would be our highest point. So if I take s of 15, I'll have 24 times 15 minus 0.8 times 15 squared, which would give me 180 meters. So there's the answer to part C. Now, on part D, how long does it take the rock to reach half its maximum height? Half its maximum height. Well, we know the maximum height is 180. So half of that, if I divide by 2, gives us 90. So what we're looking for is how long it takes. So we're looking for t. We're looking for the time when the position is 90. So my position function, s of t, needs to be set equal to 90. So we get a 24t minus 0.8 t squared equals 90. And this is just a quadratic equation, which actually surprised me a little bit when I worked it. Normally these come out nice and neat, but this one came out pretty ugly. So again, just a quadratic formula. I'm not going to waste your time. So we get 30 plus or minus 15 root 2 over 2. Now, again, that's one thing. But what the interesting thing is, you get two answers, right? Well, what do these two answers mean? One of them, when I plugged it into my calculator, I got t is approximately equal to 4.39, and the other one was approximately 25.6. So what does that mean? Well, remember, our 90 feet, if this is up to 180 right here, and our 90 feet is right here, well, you're also going to have another 90 feet off the ground on the other side. And so this one would be 4.39 seconds going up, while this one would be 25.6 seconds going down. So I always find it interesting that given the scenarios, the math always supports what should be happening in these cases. So that's kind of an interesting conclusion there. And then I'll do letter E over here. Letter E says, how long is the rocket aloft? Which is just a fancy way of saying, when does it hit the ground, right? Aloft versus hitting the ground is kind of are opposites of each other, right? So when does it hit the ground? Well, that's going to be when the position is equal to 0. So if I take 24t minus 0.8 t squared, set it equal to 0, watch what's about to happen. Wouldn't you factor out a t and set it equal to 0? And then your other one would be equal 30 when you solve that quadratic. And just like down here, how we got two different answers because it happens at two different times, we get two different answers. And the trivial solution would be at the start, right? The rock would start from the ground, be projected up, and then come back down to the ground. Hence the starting at 0 and the ending time of 30. So a really, really common example really showcases the idea of position, velocity, not so much acceleration in this problem, but we'll get there in the near future. And the last thing I want you guys to look at in this section is actually on page 126. They do a really good job in this section on giving you a visual graph of a velocity graph, in particular one that focuses not only on velocity, but you can also discuss speed as well. So there might be some problems in the homework where you see stuff like this, and on page 126 the book has a nice graph, figure 3.15, that I think you should spend a few minutes looking at.